Our next presentation is titled When Size Does Matter, an in-depth analysis of Brooklyn Bridge project data to determine the most efficient size of abrasive blast containment units and the workforce. And our presenters are Gary Van Glot. Gary is a resident engineer on the Brooklyn Bridge Rehabilitation Project. He received his formal education in the former Soviet Union and has a master's degree in engineering science from Belarusian State University of Railroad Engineers. Gary has 33 years experience in engineering and construction of buildings, bridges, and roadways, lead paint removal, and protective coatings application. He is licensed professional civil engineer in New York State, NACE 3 certified coating inspector, ICC certified structural steel bolting special instructor. His experience includes project management and analysis, field supervision, teaching, training, and instructional activities, quality control, testing, and inspection. Gary is a member of NACE International, SSPC, ICC, and AISC. And our second presenter is Timur Krasinski. Timur is a senior coatings inspector on the Brooklyn Bridge Rehabilitation Project. He holds a bachelor's degree in civil engineering and a master's degree in environmental engineering from the Cooper Union. He worked for 2 years in design engineering and 1 year in supply and construction management before getting involved in resident engineering and inspection services. Mr. Kolshinsky is NACE Coatings Inspector Level 2 certified and ICC certified as a structural steel and bolting special instructor. He is a member of NACE International, ICC, AISC, and ASCE. Let's welcome Gary and Timur.
Thank you, Mark. Good morning, ladies and gentlemen. It's a big pleasure and a great honor for us to be here today and speak on behalf of our companies Greenman Peterson Incorporated, Hirani Engineering, our client, New York City Department of Transportation, and the entire Brooklyn Bridge Contract 6 project team. Before I get to the topic of this presentation, I would like to make an announcement. This presentation is registered with New York State Department of Education for 1 PDH, so if you are interested, you can pick up the certificate at the table in front of the door, and don't forget to sign in the sign-in sheet. And it's a courtesy of GPI. I would like to acknowledge our Vice President, Jim Valenti, who is here today, who handled the processing of this certification. Thank you, Jim. So, those of you who had an opportunity to attend last year's conference and saw our previous presentation might remember some general background information about the Brooklyn Bridge Rehabilitation Project, which we called Contract 6. Today, we will talk about a very specific topic, abrasive blast containments. Walking on a bridge is always an adventure. Especially if you walk on such magnificent landmarks like a Brooklyn Bridge. After a while, you fall in love with this structure. It becomes a part of your life. You get personally attached to it. You like its beauty and majestic appearance. It is a bridge of the haunting beauty. That's how it was described in a beautiful poem of David Steinman. David Steinman was an eminent engineer and a bridge builder and who also dabbled in poetry. Steinman and his firm were also in charge of the major rehabilitation of the Brooklyn Bridge in the 1950s. Inspired by the Brooklyn Bridge beauty, he compared it with a harp against the sunset skies, a cradle for the stars, and he called it a poem stretched across the stream. Talking about the poetry, I will treat you with a few rhymes of my own later, just for entertainment purpose. But right now, I would like to hand up to Tim Kolchinsky, who is also a member of Brooklyn Bridge project team, and he will talk about some technical aspects of this presentation.
Hello, everybody. The current Brooklyn Bridge rehabilitation contract, which we call Contract 6, was bid at just over $500 million. It's just a small part of the total $2.6 billion that the New York City DOT allocated for the East River Bridges Capital Program in the wake of the I-35 West Mississippi River Bridge collapse in Minneapolis in 2007. The painting component of this contract was estimated at just over $200 million, approximately 70% of which was earmarked for the suspended spans. The suspended spans on the Brooklyn Bridge were broken up into 5 locations. Location 1 being all the underdeck support steel. Location 2 being the stiffening trusses running the full length of the bridge. Location 3 being the top struts of the bridge as well as the promenade support steel. Location 4 being the majestic main cables. And location 5, which were the suspender ropes. Locations 4 and 5, the cables and the ropes, required only minimal surface preparation. But locations 1, 2, and part of location 3 required abrasive blast cleaning to SSPC SP10 standard with total lead removal. Although what we found on our project is the contractor generally gave us an SSPC SP5, which we were also happy with. This abrasive blast cleaning required Class 1A containments to be constructed, which brings us to the point of today's talk. How big should those containment units be built? We used data from the previous 3 years of contract work to develop a formula and method for determining the abrasive blast containment unit size and workforce size that would achieve optimal results, combining the highest possible production rates while still delivering a high-quality product to the owner. Before I can delve into the technical aspects of a containment system, I should spend a minute talking about the various elements that make up a containment system. These elements can be divided into 2 categories. There are the physical components of a containment system, which is what most of you would think as the elements of a containment system. On our project, these included protective shields, vertical walls, tarps, rubber, rigging, scaffolding, and so on. But there are also these intangible, abstract components, the intellectual components. These can include the design of a containment system, its implementation, its management, its evaluation, and if needed, its modification. On our project, the containment installation began with the installation of a corrugated metal deck several feet under the bridge steel. This deck, which spans the full width of the bridge, serves several purposes. As a protective shield to prevent debris from falling into the river or onto land, creating both environmental and safety concerns. As a work platform, giving access to the underdeck steel for the workers. And, if lined with rubber, as a rigid containment base, adding another level of environmental protection. You'll notice the diagram at the bottom of the screen, which shows where we currently have protective shields on the bridge as the work is still continuing. You'll note that on the main span of the bridge, only half of the bridge has this protective shield. This is due to a requirement that at least half of the East River navigable channel be left open to the full height of the bridge, 130 feet above mean high water. The installation of the protective shield was followed by installation of vertical walls, also of corrugated metal deck, supported by either steel tube framing on the roadway or timber framing on the promenade. These were similar deck panels to what was used for the protective shield, but of a lighter gauge. They offered rigid protection between the abrasive blasting zone and the thousands of vehicles and pedestrians that use the bridge every day. The original design proposed for the containment called for full tunnel-like enclosures of both roadways. This was to be achieved with a combination of flexible materials, such as rubber sheeting and tarpaulin, and rigid materials, such as the corrugated metal deck sheets that I was speaking of earlier. This design had several issues, not least of which would be the blackout effect it would cause for portions of the roadway. Modifications had to be made. The contractor modified the design to allow for both roadways to be left open to the sky and only be protected from the sides by the vertical walls. The cross-section of the bridge was also split into 3 blasting zones. Zone 1 covering the outer stiffening trusses, Zone 2 covering much of the underdeck steel, and Zone 3 covering the inner trusses as well as that under promenade steel. The top struts were left out of the containment, and it was determined that they would be addressed during nightly lane closures. So, now that the design was modified and approved, it was time to install the containments. The contractor initially installed the platforms and vertical walls, then lined both with rubber sheeting to prevent emissions through the seams between the deck sheets. The vertical walls were then also covered with tarps to add an extra layer of protection from the abrasive media. After this was done, all the tension members, including the main cables and suspender ropes, were wrapped with rubber to prevent undue strain during the blasting process. Once the containments were built, but before blasting could commence, we had another issue that had to be addressed, and that was where to stage all this blasting equipment. This issue was exacerbated by the fact that both anchorages of the bridge are in high-density urban areas, which created concerns regarding the space that these machines take up, the noise that they generate, as well as the security of the site. These photos give a quick demonstration of how this was addressed on our project on both sides of the East River. So, the contractor initially followed their design exactly, building 100-foot-long containment units split into the 3 zones. Unfortunately, this arrangement resulted in unacceptably low production rates. The contractor was forced to go back to the drawing board and reevaluate their design to increase their production rate, looking at the length of the containment, the zoning division of the containment, as well as the size of their crew. After some experimentation, it was determined that the optimized configuration was a 45-foot-long containment unit with no zoning division. The entire cross-section of the bridge was going to be hit at once. This configuration allowed for one containment unit to be fully cleaned and primed in 4 regular shifts.
Well, I promised you some poetry, and it's a good time to start it. And if you're poor or if you're rich, you cannot buy the Brooklyn Bridge, but you can have it as a gift, but you can have it in your heart, just as a gift. Let someone turn the blasting switch, and let us hear the perfect pitch, and let us get a little kick from such a drift. So to give you some idea how the real blasting is happening under the bridge, we compiled this little video which was taken under the bridge suspended span. What you're about to see on the next slide is time-lapse animated history of the abrasive blast cleaning of the Brooklyn Bridge suspended spans. Please pay attention to this picture because few things can be changing in them, and some things are not going to change. For example, the Brooklyn Bridge is not going to move. It's still standing there where it was built by the Roblings 130 years ago, connecting Manhattan and Brooklyn sides of the East River. The date in the middle of the slide will be changing every 15 days. The vertical walls, indicated by the dark lines along the curve of each roadway, will be moving, as well as a containment zone in orange and actual blasting zone in red color. Also, the background color will be changing corresponding to the seasons of the year. So, if you're ready, I will start the next slide. Operation started with vertical wall installation on the Brooklyn half of the bridge in 2010. Contractor began installing containment units at the Brooklyn main span from the mid-span in October of 2010, followed by the blasting at the same location. Installation of containment in the main portion of the Brooklyn side span commenced in July 2011, followed by blasting in August 2011. Brooklyn half was completed in January of 2012 with walk around the Brooklyn Tower. After that, containment was removed and vertical wall was relocated from Brooklyn half to Manhattan half in January of 2012. Containment installation began at Manhattan side span from the Manhattan anchorage toward the Manhattan Tower in April of 2012, and the blasting at the same location started in July of 2012 over the land. Containment installation at Manhattan main span began in February of 2013, at mid span, moving toward the Manhattan side of the bridge, and blasting of Manhattan's main span began at mid span in April of 2013. Blasting continued through September of 2013, when it was completed, and containment and vertical walls were finally removed. And 3 years of blasting transformed the bridge steel from this condition to this. That is kind of cool. Let's do it again. From this condition to this. So, I want to tell you something. When last year, after my participation in SSPC 2013, I received an invitation from SSPC to take part in 2014 show, I was wondering what am I going to possibly write and talk about when I already gave the presentation about the entire Brooklyn Bridge contract painting project. Then I looked at our records, and as a part of my resident engineer's duties, I read, check, and sign all inspectors' reports on a daily basis. And last Friday, I was reading report number 18,000 something, and about 30% of those reports are coating inspectors' reports, which I personally sign, and the average number of the pages of the report is about 3. So for these 3.5 years, I signed about 20,000 pages with my signature, and I told myself, listen, these records we have there, have great value, and nobody's going to see them when they end up on the shelves in the New York City DOT archives. It will be a shame if we don't share this information with the world. And I told Timmy, let's do something with it. And we started to work. And the result was very interesting. Because throughout the project, meticulous records were kept on the progress of the painting. All inspectors' daily reports contain detailed information of usage, conditions, locations, etc. Information was distilled from the IDRs into tracking charts, which allowed for analysis of progress and processing of the payments. So besides all these books with the reports, we have progress charts, logs, and summaries, and several theoretical variables were derived to define production rates across various configurations. And one such variable, footprint per blaster day, was selected as the most correlated to the production rate. These units represent the average area of containment base that one blaster can clean in one regular shift. And here we go. We created this spreadsheet with all this information, with all these numbers, and we were stirring a collection of this data and tried to make sense of what we're seeing using several methods. We used algebraic analysis, graphic analysis, and magic 8-ball analysis. The man on the left side of this picture is our coating chief inspector, Mr. Sylvain Rodrigue, and maybe somebody even knows this guy in the audience. He is a very clever and experienced coating inspector, and after the few first blasts, he already predicted what would be the right size of the containment, and magic 8 balls was used to confirm that he's right, and he was right at the end. So at the end, graphic analysis was the key to understand the relationship between production rate and footprint per blaster day. And that's what we came up with. Look at this pretty picture. This picture is a history of entire Brooklyn Bridge blasting operation. The blue bars represent containment size in feet, and red bars production rate and footprint per blaster days. As this diagram demonstrates optimal production, we observed when the containment length was set to 45 feet, which equals 6 panels of the bridge, and the entire cross-section of the bridge was blasted at once. You can see at the end of the blasting, it became very consistent and even jumped up a little at the end. And there was a reason for that. Well, our project was affected by several disasters, both natural and otherwise. These events caused significant delays due to damage they inflicted on the job site. These include the Virginia earthquake, the Hurricane Irene, which took place the same year of 2011, a crane collision in March of 2012 when 130-foot crane and a barge collided with and severely damaged one of the protective shields, leading to the entire platform being condemned. And finally, the Hurricane Sandy, which hit New York City at the end of 2012. Well, but the project wasn't always a disaster. We managed to celebrate some personal milestones, such as 3 birthdays each, including my 50th birthday and Tim's 25th birthday, and some other personal milestones. One of my daughters got married, I got 2 new grandchildren, 2 of my younger daughters graduated from the high school, and my personal budget survived 2 prom dresses. And Tim graduated from the master's program in 2011, so his personal life was not that eventful because he's still single and available. So, ladies and gentlemen, if you have daughters of his age, pay attention to this young man who has a great potential. And he will continue this presentation now.
After analyzing the data, we had to develop a formula to explain the results. The first thing we did was determine what our fixed parameters were. In our case, the width of our bridge, 90 feet. We also determined from the graphic analysis that 8 blasters is optimal for the geometry of our structure. And we knew that the ideal blast cycle that we were looking for was 4 days. So what we did was we divided the width of our bridge by the number of blasters to get our WPB, the width per blaster, of 11.25 feet. And then using some stoichiometric principles, we were able to derive the formula that the length of your containment should equal your footprint per blaster day times your ideal blasting cycle divided by the width per blaster. Now that a formula was developed, it can be applied to many similar structures. What you would do is you would take your width per blaster to equal 11.25 from empirical observations. You would assume a blasting cycle of 4 days, and then you would determine your footprint per blaster day based on the quantity and intricacy of the structure and your knowledge of a blaster's rate of work. This is based on your professional experience. You would then calculate the length of the containment. And while doing that, adjusting your width per blaster and your blast cycle as needed to accommodate the specific job requirements that you're dealing with. At this point, I'd like to hand off back to Gary to bring us home.
So, ladies and gentlemen, the formula is just like a musical instrument. If you don't know how to play it, it's not going to make a good sound. If you have your performance skills mastered, and it will produce a beautiful melody. It is up to us how we use our tools, instruments, and skills on the road way of life, which is filled with bridges connecting places, souls, and hearts. Sometimes we burn them behind us to go on to live, suffer, hope, and love, and believe that our dreams will come true. By painting the bridge, we preserve it for the future generations and make a connection between the future and the past. Ladies and gentlemen, I would like to conclude this presentation with a few more rhymes dedicated to all bridge painters, builders, and inspectors. We're reaching out for a star. We know already who we are. We're living life la vida loca, having a blast. We're breathing wind and touching sky. It's our fate, and that is why we're building bridges to the future from the past. Thank you very much. any questions? Yes.
How did you address the contact point of the containment with the main structure for the blasting or painting and that? Because you have a lot of hangars and all which were contacted with the structure.
Oh, it's going to be addressed as a part of the punch list work after the platform is removed.
How you, after all the paint was done, all those contact points, you took care of
Well,
it?
some of them were moved and shifted during the transitional periods between intercodes, and they're already addressed. However, this project is not still ongoing, and the completion inspection is not performed yet. After it's done, we will address them on a local basis.
My point is that those contact points haven't been blasted. So
No, they
after,
The contact points are primarily handled on our project using power tool cleaning locally, and with a slightly different paint system because we use a zinc primer which should not be used for power tool cleaning. With the contact points, we use a different primer, an aluminum primer, and address them on a point-by-point basis.
okay.
I hope that answered your question, sir.
Yeah, it answered, but those are the weakest point, and that is start rusting very, very fast. All those contact points.
That's what we
That's
call jobs.
why
That's what we call job security, sir.
I am from New Jersey Department of Transportation, and I eliminate if I can, all the contact points with the beams, with the structure at all. Only I allow on those diaphragms or cross frames.
And we didn't mention it, but minimizing the contact points was a concern that was handled throughout the process.
Okay, pretty good, thanks.
If you want to catch up with these guys at the end of the session to handle some more questions for you, that'd be great. We got to kind of get rolling here. Nothing getting this one right.